Hello guys, I welcome you to my YouTube channel, and this is IBM. Many people ask what IBM stands for. Those are simply initials of my name, Ivan Brian Mulumba. So today I would like to take you to I think this is going to be part 5 of our solved past paper questions. Remember, we are dealing with AS physics. These are multiple choice questions. MCQ stands for multiple choice questions. This is Physics 9702. I'll be recording videos for paper 5 for some students ask me to record some paper 5, especially question number 2. But I'll record videos for paper 5 for both question number 1 and question number 2 to show you how you approach that paper. So remember, this is kinematics and dynamics, and this is specifically going to be part 5. So let's start. Let's start from where we stopped. So in part 4, I think we stopped on this page, page 34, and in part 5, I want us to start from the same question that's from the last question on this page. The diagram shows a particle P traveling at speed v about to collide with a stationary particle Q of the same mass. The collision is perfectly elastic. So that means relative speed of approach should be equal to relative speed of separation. So if the collision is perfectly elastic, we are saying relative speed of approach should be equal to the relative speed of separation. The relative speed of approach, since one was stationary and the other one was moving, the relative speed of approach is v minus 0, which is v. So it means the relative speed of separation should also be v. Relative speed of separation should also be v for collision to be perfectly elastic. So let's check the possible which statement describes the motion of P and Q immediately after the collision. So P and Q both travel in the same direction with that speed. So this one means the relative speed of separation is a half v minus a half v, which is 0. So this one is out. P comes to rest and Q moves with the speed v. So relative speed of separation is v minus 0, which is v. And I think it means, or it implies, or it simply means the answer is going to be B. We can check P rebounds with the speed a half v and Q acquires speed v. P rebounds with the speed v, a half v. That means it's going to be negative. And Q acquires speed a half v. That would mean it has given half to the other one and it has remained with the half. But the challenge is which direction does Q move? So this one, the most appropriate answer is going to be P comes to rest and Q acquires a speed v, because if the collision is perfectly elastic, total momentum before collision should be equal to total momentum after collision. So, and then the relative speed of approach should be equal to the relative speed of separation. So this for B, total momentum before collision would be m, or 2m. Sorry, it is m plus m times v. That is total momentum before collision. Total momentum after collision should also be m times v. But for C, total momentum before collision is m times v, yet total momentum after collision is going to be different because one has speed half v, the other one has speed a half v. So total momentum after collision is not going to be conserved. It is most likely not going to be conserved. So the answer is going to be P, because for P, total momentum after collision is still v, mv, and the relative speed of approach is the same as the relative speed of separation, which is v. A car travels along a straight horizontal road. The graph shows the variation of the velocity v of the car with time t for 6 seconds of its journey. The brakes of the car are applied at t equals to 1. So at t equals to 1, the brakes are applied here up to t equals to 4. How far does the car travel while the brakes are applied? So how far is distance? So we want the area and that part of the graph. So that distance, if we take it as I can just use, since it is a straight line, the acceleration is constant, I could just say, okay, S is going to be U plus V divided by 2, then times T. So this will be, U is, I think this is 22, and this is going to be 8. So we have 22 plus 8 divided by 2, and the time is 4 minus 1, which is times 3. So this gives us an answer which is 30 by 2, which is 15, times 3, which is 45 meters. Alternatively, you could use a v squared equals to u squared plus 2as, where v, final velocity, is 8 squared, initial velocity is 22 squared, plus 2 times the acceleration. Of course, we are times the acceleration times s. But remember, we can find acceleration from v minus u over t, where v is 8 minus u, which is 22, over t, which is 3. So this is 8 minus 22, which is, I think that is it 14 minus 14 over 3. That will be the acceleration. So you can substitute the acceleration, that expression, and you find s. Remember, the acceleration will be negative, so it will take you to the same answer. So the answer is going to be B. You could also use s equals to ut plus a half at squared if you have the acceleration, but the answer will be the same. We could just take the area under the graph, which will be it will of course be a trapezium, and taking the area under the graph is what leads me to this expression here. A stone is thrown horizontally from the top of a cliff and falls into the sea. Some time later, air resistance is negligible. This is very important. If air resistance is negligible, then acceleration is going to be constant. Which graph shows how the vertical component v vertical of the velocity of the stone varies with its horizontal component vh of velocity as it moves through the air. So the horizontal component must remain constant as the vertical component increases, and will increase uniformly since the acceleration in the vertical is constant for no air resistance. So C is automatically wrong because it shows that the vertical component remains constant. Yet when a body is falling, the vertical component of velocity in the vertical increases. So C is wrong. B shows it increases and it is becoming constant. It can't become constant in the vertical because air resistance is not considered. So the acceleration remains constant. A is also wrong because it shows that the acceleration in the vertical increases. So the answer is going to be D, because velocity in the vertical is constant, that is a vertical line, but velocity in the horizontal the velocity in the vertical is increasing, so we'll have the line going upwards in the vertical, but in the horizontal it is not changing, it is just at a fixed value. So velocity in the vertical remains constant, velocity in the horizontal is constant, because the only force acting is in the vertical, that is force due to gravity. Velocity in the vertical is the one which increases. So the answer is D. A positive charge 2.6 times 10 power minus 8 coulombs is in a uniform electric field of field strength 300,000 volts per meter. How much work must be done on the charge in order to move it a distance of 4 millimeters in the opposite direction to the direction of the field? Of course, this is electric field is no longer in AS, but I will still answer this for completeness. So work done is supposed to be force times distance, but work done is the same as difference in kinetic energy. Also remember, the electric field strength is defined as the force per unit charge, which implies that the force is going to be charge times electric field strength. So I can still say that the work done is going to be the force, which is the charge 2.6 times 10 power minus 8 times electric field strength, which is 300,000, then times distance, because force is QE. The distance is 4 millimeters, so that will be 4 times 10 power minus 3. So I'll check with my calculator. 2.6 exponent minus 8 times 300,000 times 4 exponent minus 3. So that is 3.1 times 10 power minus 5. 3.1 times 10 power minus 5 joules. So the answer is going to be A. Each diagram illustrates a pair of forces of equal magnitude. Which diagram gives an example of a pair of forces that is described by Newton's third law of motion? Newton's third law of motion. Okay, so remember Newton's third law. The force on a body A should be equal but opposite the force on body B. So let's check these forces. Remember, the two forces must act on different bodies. So A is out because these two forces are acting on the same body. The two forces must be acting on different bodies. This one is also going to be out because these forces must be acting in the same plane. So they should be in the same plane or in the same line. And also, if the weight is acting vertical downwards, then the force acting on the support should be coming from the center of the object onto from the center of the play of the support the object. So the answer is going to be automatically B. Why? Because the moon pulls onto the earth by this force here, and the earth pulls onto the moon by this force. These two forces are equal but opposite. They're in opposite directions and they're acting on two different bodies. So the answer is going to be B. Of course, D is going to be wrong because it gives an impression that the two forces are acting on the same body, yet they should act on different bodies. So D is also out. Remember, for Newton's second law, the two forces are equal but opposite in magnitude. That's number one. Number two, these two forces do not act on the same body. They act on two different bodies. So the answer is going to be B. A stone is dropped from a tall building. Air resistance is significant. Air resistance is significant. That means acceleration is not constant. In fact, the acceleration must be decreasing. The variation of distance falling with time t is shown. So since this is distance, the gradient should be velocity. Gradient equals to velocity. The gradient equals to velocity. So it means since it is falling in air where the acceleration decreases, there should be a point where the gradient should become constant. So the gradient should become constant. Should become constant. If it becomes constant, it means velocity is going to be constant, which would mean acceleration becomes zero. So V is velocity is the gradient. So let's check. A is wrong because A shows that the velocity is constant throughout, which means acceleration is zero. So this one means acceleration is zero throughout. B, the gradient is initially zero, then it increases and it becomes constant, which means initial acceleration is zero, then acceleration increases. Sorry, the velocity is initially zero because the gradient is initially zero. Then all of a sudden the gradient increases, which means the velocity increases and becomes constant. But remember, this was the path of the first stone. Also remember that. So that means if there is air resistance, the maximum velocity cannot be above. So that makes B to be low, to be wrong. So it means the velocity should be less than the initial velocity if there was the initial velocity for the first stone. Because a second stone with the same dimensions but a smaller mass is dropped from the same building. Okay, so smaller mass, it should be having a smaller terminal velocity. Smaller mass. Smaller mass means, since they have the same dimensions, smaller mass means smaller terminal velocity. So it means the gradient should be constant with time, but the gradient should be less than the first path, the first stone. So the answer should be between C and D. Now what makes D wrong is that D is a straight line throughout, which means the velocity is constant throughout, which means there was completely no acceleration. So means the answer is C, because initially the velocity increases. Initially the gradient increases, but with time the gradient becomes constant. That means the velocity increases to a constant value where the acceleration decreases to become zero. So the answer is C. We have reached terminal velocity. A helium atom of mass m collides normally with a wall. The atom arrives at the wall with speed v and then rebounds along its original path. Assume that the collision is perfectly elastic. Perfectly elastic. What is the change in the momentum of the atom during the collision? So it collides with the wall. Its initial momentum is mass times velocity. It rebounds. The relative speed of approach is the same as the relative speed of separation. So the speed with which it rebounds, it is v. So its momentum is m times v in the opposite direction. So the change in momentum is going to be mv minus negative mv, which is equal to twice mv. So the answer is going to be D. The graph shows how a physical quantity varies with time. Which event could best be represented by graph G? So we are seeing the quantity decreases with time. It remains zero for some time and then changes direction, and then it decreases, changes direction, increases rapidly to maximum value, then it decreases. So this is most likely going to be acceleration of a skydiver, because this part here is showing that the resultant force is now up, now in is opposite. This one shows the resultant force. F resultant is now opposite to the motion. So which makes A to be a negative value. I think that is the motion of a skydiver. So quantity A, the acceleration of a skydiver leaving an aircraft. If it's falling in air, it means the acceleration decreases and it becomes zero when it reaches terminal velocity. But remember, air resistance is increasing. When he opens the parachute, then the resultant force changes direction because there will be more air resistance in the opposite direction. So it means the resultant force changes direction, the acceleration becomes negative. So what happens is that it decelerates, or it slows down, or its velocity slows down. That's why now we are seeing the gradient is positive, but it is tending to zero. So the answer is going to be B. The answer is going to be B. V is A was saying the acceleration of firework rising to a maximum height. Of course, at a maximum height, V becomes zero and falling to the ground. So if it is raising to, if you say it is acceleration of fireworks raising to a maximum height, a will be negative. So this means this will mean the okay, the gradient is negative, but this will be v. So that means the answer is going to be b. It cannot be a. The acceleration of a firework raising to maximum height. If this is the acceleration, acceleration is going to, if the quantity is acceleration of a firework raising to maximum height, then it means I don't think the acceleration is going to be decreasing when it is raising and then falling. No, the answer is going to be A. I mean, the answer is going to be B. The acceleration of a skydiver leaving an aircraft, falling, opening a parachute. At this point where he opens the parachute, the air resistance becomes greater than his weight. So the resultant force changes direction. That's why I said this part here shows opposite. The resultant force is in the opposite direction to motion. So the acceleration becomes negative. So the answer is B. What describes the mass of an object? So mass is the amount of matter in a substance. Mass is the force the object experiences due to it's actually the opposition or a property of a body to resist change in its motion, that is mass. So the answer here is automatically going to be C. The resistance of the object to changes in motion, that is mass. A car has mass m. A person needs to push the car with a force F in order to give the car an acceleration A. The person needs to push the car with a force twice F in order to give the car acceleration 3A. Which expression gives the constant resistive force opposing the motion of the car? Constant resistive force. Okay, let the resistive force be Fr. Let the resistive force be Fr. For the first person, the resultant force, which is given by Newton's third law, Ma, is going to be the force he uses F minus the resistive force Fr for the first person. And if he uses the second force to twice F, so it means by Newton's second law, and remember the acceleration is 3A, so I'll say m into 3A, that is the Newton's second law, should be equal to the force he uses, which is twice F, minus the frictional force, which is Fr. So I have this equation and this equation here. So what I'm going to do, I'm going to subtract the two equations. I'm going to subtract the two equations. So I'll have 3ma minus ma should be equal to twice F minus Fr, then minus twice F minus Fr, then minus F minus Fr, F minus Fr. So 3m, that is, I think that is ma equals to twice F minus F. No, I have to multiply 1 by 2 so that I can easily, so I'll multiply this by 2. So times 2, that is twice ma. Then these ones should also be multiplied by 2, okay. So we have twice F minus 2F, it cancels out. Then I have minus Fr, minus and minus, so it is plus twice Fr. So it means Fr is going to be equal to MA. So the answer is going to be A. So I just combined, I multiplied this equation by 2, and then I subtracted it from this one, and I'm getting Fr equals to MA. The graph shows the variation of velocity v with time t for an object. Okay, the object passes a fixed point at time t equals to 0. What is the displacement of the object from the fixed point at time t equals 5.0 seconds, and what is the acceleration of the object? Okay, so for acceleration is the gradient. So acceleration is equal to the gradient, which is going to be v minus u over t. V is 24 minus u, which is 4, divided by t, which is 5. So that is 20 divided by 5, which is 4 meters per second squared. So acceleration is 4 meters per second squared, which eliminates C and D. Then displacement is the area under the graph. Displacement is the area under the graph. So S is going to be equal to a half. This is a trapezium. So what would be like A would be this one. This would be B. So A is 4. B is 24. Then times, area of a trapezium, a half. A plus B times H. So S is a half into 4 plus 24. Then what would be like the height is going to be this distance, this one here, which is 5. So this gives me, that is 28, which is 14 times 5. I think 14 times 5 is 70 meters. So the distance displacement is 70 meters, which makes the answer to be B. A skydiver jumps from an aeroplane and falls vertically through air. If he falls through air, the acceleration must decrease to 0, and the velocity must become constant with some time. So which graph shows the variation with time of the skydiver's vertical velocity? Vertical velocity. This one shows the acceleration is constant, yet it decreases. Acceleration is constant. This one shows that the gradient is decreasing. Remember, the acceleration equals to the gradient. And we have said if you are falling in air, the velocity, if you are falling in air, the resultant force decreases. Remember, the weight is going to be equal to the resultant force is equal to the weight minus the force due to air resistance. If you are falling in air, air resistance goes on increasing until the weight equals the force due to air resistance, which makes the resultant force to be 0, which makes the acceleration to be 0, which makes V to be constant. So V should be becoming constant, so the answer is going to be C. The gradient decreases, which means the acceleration tends to 0. D is wrong because the gradient increases, which means the acceleration is increasing. A nucleus collides with a stationary nucleus in a vacuum. The diagrams show the paths of the nuclei before and after the collision. No other particles are involved in the collision. Which diagram is not possible? Not possible. Okay. So I think that the diagram which is not possible is going to be C, because remember, momentum must be conserved. And for C, if I complete a horizontal line, it means momentum in the vertical cannot be conserved, because here it means there's a resultant momentum downwards. In the vertical, there's a resultant momentum. In the horizontal, we can resolve these to form momentum in the resultant in the horizontal, but there's no component in the vertical to balance this. There's no component in the vertical to balance the momentum downwards. So the answer is going to be C. Reason, there's no component up to cancel out the components down. So we say that momentum in the vertical is not conserved. Momentum in the vertical is not conserved. For the rest, you notice that, remember, the nucleus was moving in the horizontal, so total momentum should still be in the horizontal. For A, there's a component upwards to cancel out the one which is downwards. For B, if I draw a horizontal line here, still there's a component downwards caused by this one to cancel out the component upwards caused by this one. For D, if you try to draw a horizontal line here, you will still see that this line here is above the horizontal, so there's a component in the vertical. Cancel out the component in the vertical by this one, so it is only C where there is no component upwards to balance out, to cancel out the components downwards. So the answer is C. The velocity of an electric car changes as shown. What is the acceleration of the car? What is the acceleration of the car? Of course, acceleration is the gradient. So acceleration is equal to V minus U over T. So V is, I think that is 105. This is 105. U is 0. And then T, remember this is kilometers per hour. So this should be times, to change it to meters per second, this would be times 1000. Then T times, okay, it is kilometers per hour, so it is times 1000 over 3600 to change it to meters per second. Then T is 4 seconds, so this is going to be divided by 4. So I have to press my calculator. 105 times 1000 divided by time is 4. But remember, I had to convert from kilometers per hour to meters per second, so times 3600. So this is giving me 7.3. So the acceleration is 7.3 meters per second squared, which is D. A projectile is fired from point P with velocity V at an angle theta to the horizontal. It lands at point Q, a horizontal distance r from P, after time t. The acceleration of free fall is g. Air resistance is negligible. Which equation is correct? I think we have solved a similar equation. So remember S, I'll just use S equals to ut plus a half at squared. Remember, acceleration in the horizontal is 0. So if I use acceleration in the horizontal as 0, then r is going to be, resolve v in the horizontal, it is v cos. So this will be v cos of theta, then times t. Acceleration in the horizontal is 0. If I consider vertical motion, if it leaves P and comes back to Q in the same horizontal line, S will be 0. So 0 equals 2. I'm resolving V in the vertical, which is V sine theta in the vertical. In the horizontal was V cos theta. So U is going to be V sine of theta, then times T. Because it is moving against gravity in the vertical, acceleration in the vertical is going to be negative G. So this will become minus a half times G times T squared. So 1T cancels out, 1T is cancelling out. So I'll just have that V sine theta is equal to a half G times T. But I can make T the subject. T is going to be, in this equation, T is R over V cos theta. So V sine theta is equal to a half times G times, where there is T, I'm putting R divided by, V cos theta. So first of all, this equation is correct. R is Vt sine theta. This is wrong. R is, of course, the only correct equation would be this. So of course, if I try to make R here the subject, R is going to be 2V squared sine theta cos theta divided by G. So we don't have that equation here. So the only correct equation is A. A car accelerates from rest in a straight line with constant acceleration. Which graph from rest with constant acceleration, that is a horizontal line? Which graph best represents the variation of the momentum P of the car with the distance S traveled by the car? Momentum with distance. Okay. I want you to recall that force equals to the rate of change, or resultant force is the rate of change of momentum, which can be m into v minus u divided by t, where v minus u divided by t is the acceleration. So for an acceleration, v is supposed to be increasing. Because it has an acceleration, v must be increasing. So for an acceleration, v must be increasing, so p must be increasing. So for an acceleration, velocity is increasing. So v minus u is positive. So that means momentum must be increasing. The momentum must be increasing because for an acceleration, v increases, so the momentum should be increasing. And also remember, momentum is mass times velocity. Momentum is mass times velocity. So we have already ignored d because d is showing momentum is constant. Momentum must be increasing. So we ignore d. Momentum is mass times velocity, but if we use equations of motion, since the acceleration is constant, v squared is equal to u squared plus 2as. V squared equals to u squared plus 2as. It started from rest, which means v squared is equal to 2as. And when you look at this equation here, it means v increases more rapidly as s increases. So it is not a straight line. If v squared is equal to as, it means v increases more rapidly than s. So it can't be a straight line, so ignore b. Not a straight line. Not straight. Because v is squared and s is not. So it means v increases more rapidly as s increases. So it can't be a straight line. Then from momentum equals to mass times velocity, it means momentum is going to be mass times the square root of, because v is the square root of 2as, which means momentum is directly proportional to the root of s. And that equation, that graph is going to be a. If momentum is directly proportional to the root of s, it means you can check with the values. If s is 0, momentum is automatically 0. But if s is 1, momentum is the root of 1. If s is 4, then momentum is the root of 4, which is 2. So the graph has a decreasing gradient. So the answer is going to be 8. It can't be C, because C has an increasing gradient. Yet as s increases, momentum increases as the square root of s, which means the gradient should be decreasing. So the answer is going to be A. So this one means decreasing gradient. This is decreasing gradient. The resultant force F on a raindrop of mass m falling with a velocity v is given by that equation. K is a constant and g is the acceleration of free fall. What is the velocity of the raindrop when it reaches a constant terminal velocity? Remember, terminal velocity acceleration is 0, resultant force is 0 at terminal velocity. So that means the resultant force, remember, is given by ma, but should be 0. So they told us the resultant force F on a raindrop of mass m falling with velocity v is given by that equation, where k is a constant and g is the acceleration of free fall. What is the velocity of the raindrop when it reaches a constant terminal velocity? So before it reaches a constant terminal velocity, the resultant force is given by ma, which is going to be equal to mg minus k times v squared, which means of course, if it has reached a terminal velocity, it means v, so this will be 0. So it means kv squared is going to be mg, which means v is going to be the square root of mg divided by k. So it means my answer is simply going to be C. If it reaches terminal velocity, it means the resultant force is 0, acceleration is 0, so kv squared is equal to mg, making v the subject, that will be the square root. So the answer is C. A stationary toy gun fires a bullet. Which statement about the bullet and the gun immediately after firing is not correct? Immediately after. The force exerted on the bullet by the gun has the same magnitude as the force exerted on the gun by the bullet. That is Newton's third law, which is correct. But they said is not. The force exerted on the bullet by the gun is in the opposite direction. That is also correct. That is still Newton's third law. The gun and the bullet have the same magnitude of momentum. That is conservation of momentum. It is the same magnitude of momentum but in opposite directions. The kinetic energy of the gun must equal the kinetic energy of the bullet. So this one is not going to be correct because the question is a stationary toy gun fires a bullet. Which statement about the bullet and the gun immediately after firing is not correct? Remember, total kinetic energy before was 0, and yet after firing, total kinetic energy is no longer 0. So kinetic energy is not conserved. EK not conserved. So this one is not correct. Kinetic energy is not conserved. Immediately after firing, it was stationary, so initial kinetic energy is 0. After firing, it is not 0, so kinetic energy is not conserved. A wooden block rests on a rough surface of a board. One end of the board is then raised until the block slides down the board at constant velocity v. What describes the forces acting on the block when it is sliding? When it is sliding with constant velocity. I want you to get used to the fact that at constant velocity, acceleration equals to 0. If acceleration is 0, the resultant force is 0. So if it is sliding, of course, we have a force upwards, and we must be having friction force in the opposite direction. There's a force downwards and friction force in the opposite direction, which makes the resultant to be 0. So the resultant must be 0. So we ignore A and D. It is showing that the resultant force on the block is down the board. So it should be 0. But the frictional force must be in the opposite direction to motion, so it should be upwards. So the answer here is going to be D. Friction upwards. Of course, if this angle is known as theta, this force will be mg sine of theta. So the difference should be 0 for constant velocity, where the resultant is 0, acceleration should be 0. The graph shows how the velocity of a ball varies with time from the moment it is hit vertically upwards from the ground. What is the displacement of the ball from the ground after a time of 3 seconds? Okay. What is the displacement of the displacement of the ball from the ground after t seconds? Of course, the first area, the ball is moving upwards because the velocity is decreasing. Then the second area, the ball is moving downwards. Here, it is at maximum height at this point here. But we see that this area is not the same as this one, so it doesn't return to the same position. So what is the displacement of the ball from the ground after 3 seconds? So we want this distance here. Because if it leaves this level from the ground, it is not reaching the same level because the areas are not the same. So we shall just subtract, find a difference, that will be the displacement. The displacement to the maximum height is going to be a half times 2 times 20, that is area under the graph. Then we subtract the displacement when it is falling downwards, or the distance downwards, which is a half, times the base could be 1, 3 minus 2, and the height could be 10. So this gives me 20 minus 5, which is 15 meters. So the answer is A. Two students each throw a ball horizontally from the top of a tower. The two balls are released at the same time. The first student throws her ball with a speed of 20 meters per second, and the second student throws his ball with 10 meters per second. Assume air resistance is negligible and the balls land on horizontal ground. Which row describes the horizontal distance traveled and the landing times of the two balls on the ground? Okay, both balls are projected horizontally. The two students each throw a ball horizontally from the top of a tower. So I will sketch something here. Let this be the top of the tower. So one ball is 20 meters per second. Another ball is 10 meters per second. So which row describes the horizontal distance traveled and the landing times of the two balls on the ground? Okay, so if I consider horizontal motion, R is going to be different. If you consider horizontal motion, in the horizontal, R is equal to, okay, using S equals to UT plus a half at squared. In the horizontal, A in the horizontal is 0. So this part will be 0 for horizontal motion. So R will be U times T. Since U is the same, since U is different, then R is most likely going to be different. Because there is no air resistance, R depends on speed and thus depends on also on the time. But then if I use S, if I consider vertical motion to check the time, they are going to follow the same vertical distance. Because if I consider vertical motion, they follow the same vertical distance. So S in the vertical is going to be initial velocity in the vertical, which is 0 times t plus a half at squared, which is a in the vertical. So the same vertical distance, S in the vertical, is equal to this part is 0. So this is a half times g times t squared. Since this is the same and g is a constant, then t in the vertical is the same. So t, of course, t is going to be twice sy divided by g under square root. So t is the same. T is the same. It doesn't depend on u. T is the same. Does not depend on u. The time is not depending on u. So t is the same. But remember, r is equal to u times t. And u is different. T is the same. So it means r is going to be different. So r is different. Because r is depending on u, even though t is the same. So landing time is the same. The landing time is the same, but the horizontal distance is different. So the answer is going to be C. Landing time is the same, horizontal distance is different. Ball of mass m travels vertically downwards and then hits a horizontal floor at a speed u. It rebounds vertically upwards with speed v. The collision lasts at time delta t. What is the average force? So by definition, force is the rate of change of momentum. So its mass is m, initial velocity is u, it rebounds with velocity v. So one velocity, if falling is positive, then rebounding must be negative. So negative v. So the difference, the change is going to be u minus negative v. Then divided by time is given as delta t. So this becomes m into, or mu plus mv divided by delta t, which makes our answer to be automatically D. And of course, this is upwards because It is not downwards because the motion is upwards on rebounding, so the answer is D. It is not A, it's not C. Because the final moment, the velocity is upwards after rebounding, so the change in momentum is upwards. So the answer is D. The resultant force acts in the same direction as the change in momentum. The resultant force F on a raindrop of mass m falling vertically with velocity v is given by that equation, where k is a constant and g is the acceleration of free fall. The falling raindrop eventually reaches constant terminal velocity. Which graph shows the variation of terminal velocity of the raindrop with mass? Terminal velocity. Okay, so at terminal velocity, resultant force becomes zero because acceleration is zero. Resultant force is zero because acceleration is zero when velocity is constant. So it means k times v squared, which v is going to be terminal velocity, is going to be mg. So it means terminal velocity is going to be the square root of mg divided by k. So let's try to just do inspection. It is a graph of m, terminal velocity against m. So it means when m is 0, v should be 0. When m equals to 0, terminal velocity should be 0. So it means we ignore a because it doesn't start from 0. We also ignore c, doesn't start from 0 because when a is 0, v should be 0. So we have to choose between b and d because b is initially 0. When m is 0, v is initially 0, but then it starts, the gradient starts decreasing. And this, as m increases, v is equal to the square root of mg over k. So this is showing for this point here, of course, b and d, one of them could be correct, but let's check the gradient. So we notice that v, terminal velocity, is directly proportional to the square root of m. What does that mean? Of course, we have seen an example like this one, that this is a decreasing gradient. So this is a decreasing gradient. D shows an increasing gradient, that's what makes it wrong. Yet as m increases, if m is set 4, v is going to be the root of 4, which is 2. So it is a decreasing gradient. So the answer is going to be B. I gave an example when if m is 4, which is big, v is going to be the root of 4, which is 2. If m is equal to 9, v is going to be equal to root of 9, which is 3. That is a decreasing gradient. So the answer is B, not an increasing gradient. A ball of mass m moving at velocity v collides with a stationary ball of mass 2m. The two balls stick together. So they move with a common velocity. Which fraction of the initial kinetic energy is lost on impact? Okay, so let's find total kinetic energy. Let's first find the velocity before. So initially, one is moving, one is at rest. So for conservation of momentum, initial momentum is mv. Total momentum, since they stick together, total mass will be m plus 2m, which is 3m. Let the velocity be vx after collision. So it means the new velocity vx is going to be 1 over 3 times v. So initial kinetic energy, I'll call it E1, is going to be a half times mass m times v. Because the other one was at rest, so it is only this one which had kinetic energy, v squared. That is initial kinetic energy. Then kinetic energy after the impact, E2, is going to be a half. Total mass is 3m. Then total velocity is 1 over 3 times v, but this is squared, 1 over a third v squared. So this becomes 3m over 2 times v squared over 9. So 3 cancels, so it becomes mv squared divided by 6. mv squared divided by 6. That is the new kinetic energy. So let's find the change or the difference in kinetic energy. So the change in energy is going to be a half mv squared minus 1 over 6 mv squared. So I just subtract 1 over a half minus 1 over 6. So 0.5, that is a half, minus 1 divided by 6. So that is 1 over 3. So this is a third, mv squared. So that is the change in kinetic energy. But then what fraction of the initial kinetic energy is lost? So we want the fraction. So the fraction is going to be a third, mv squared, divided by the initial energy, which was a half, mv squared. The initial energy, which is E1, is a half mv squared. So this becomes 2 over 3. So the answer is going to be C. Because mv squared cancels, a third divided by a half is 2 over 3. The stone is dropped from a height of 20 meters above water. The graph shows the variation with the time of the velocity of the stone. Which statement describes the approximate position of the stone 4 seconds after it is dropped? 4 seconds after it is dropped. So at this point here, it must be hitting the water. Here it hits. It hits the water. That's why the velocity rapidly decreases to 5. So it hits the water and v rapidly decreases. And now it is constant. So here, if it is constant, now it must be in water. V decreases, now constant in water. So here V must be in if it hits the water and V decreases, we are now seeing a constant velocity, so it is now in water. So which statement describes the approximate position of the stone 4 seconds after it is dropped? So let's first find S to reach the water, S to reach the water surface. That is the displacement to reach the water surface is the area under that graph, which is this one here. So it is a half times the base, which is 2, times 20, which is 20 meters. So it has traveled 20 meters to reach the water surface. Then S while in water, the distance it moves when it is in water, S while in water. The distance while in water, this is the distance while it is in water. So it is 5. This is 2 and this is 5. So it is 5 times 2, which is 10 meters. So that is the distance while it is in water. So it is simply going to be 10 meters below the water. Because it travels a distance of 20 meters before to reach the water. And then the distance while in water is 2 times 5. So this is the distance it covers while it is in water. So which statement describes the approximate position of the stone 4 seconds after it is dropped? It is at a distance of 10 meters above the surface of water, not at all. It is below the water. It is at a distance of 10 meters below the surface of the water, so the answer is B. It is at a distance of 20 meters below the surface of water, not at all. It is at a distance of 30 meters below the surface of the water. That is not true. It is 30 meters below the point of the point from which it was thrown, but it's not 30 meters below the surface of the water. It is just 10 meters below the surface of the water. A car X traveling at a speed U along a straight road at time t equals to 0, a second car Y is distance d naught behind car X, and traveling at speed v in the same direction. Speed v is less than speed u. At time t equals to 0, car y begins to accelerate with a constant acceleration. Car y overtakes car x at time t equals to t. So at t equals to t, there is overtaking. Which graph best shows the variation with time t of the distance d between the cars? Okay, so the distance d between the cars. So I first of all sketch a graph of velocity with time. So let me draw velocity is a vector quantity against time. So this is v with t. So remember, car x is traveling at a constant speed. So I'll draw a horizontal line for car x. Let me use this color for car x, constant speed. That is for x. This is x. At time t equals to 0, second car y is distance d naught behind car x and traveling with at a speed v in the same direction. Speed v is less than, so the graph should be below. Because v is less than, starts with a smaller speed, so I'll use a different color for that one. Speed v is less than, but remember at time t equals 0, car y begins to accelerate, so the speed should be increasing. So speed y for y should be increasing. Okay? Since it is a constant acceleration, it is also a straight line, so this is for y. Car y overtakes car x at time t equals to 0. Car y overtakes car x at time t equals to 0. I mean at time t equals to capital T. So here, this part here before this part here, let me just put here values. So this one is, they are further apart, they are far apart. So here they are further apart. Here they are further apart. Then the speed, when the speed of y is equal to the speed of x. At this point, the speed of y is equal to the speed of x. So this region here, let's say there is catching up somewhere here. So here we have catching up. And if you look at s equals to ut plus a half at squared. If you look at s equals to ut plus a half at squared, for car y, which has a constant acceleration, did it start from 0? At time t equals 0, second car y is distance d naught behind car x and traveling at speed v. So its initial speed is v, then it accelerates. Okay. So which graph could best show the variation with the time t of the distance d between the cars? So d is going to automatically be wrong because it shows that there's 0 acceleration for both cars. Because d, it is showing that as time goes on, the distance between them decreases, but at 0 acceleration. In other words, this is showing 0 acceleration, so this is out. And this one is showing that the acceleration is not constant because initially the acceleration is constant for a horizontal line, then the velocity, the gradient is increasing the opposite direction. So this one is showing that the acceleration keeps changing. So this one also not correct. So this is showing A keeps changing because V, the gradient keeps changing. So A keeps changing. Remember, the gradient is going to be the speed. Then, so it means this is also going to be out. Here the acceleration, here it is showing that the velocity remains constant for some few seconds, for some time, and when the velocity slightly increases, then it decreases. I mean no, it's like it moves it moves backwards before it moves in the direction towards x. But then look at this part here, the gradient is almost zero, so that means velocity remains zero for some time. So here the velocity remains zero for some time. So the answer here is going to be B, because since V could initially be less than U, the value of V could initially be less than U, the cars will initially get further apart until must initially get further apart until V is equal to U, then they tend to catch up. So this part here is going to show that the cars initially get further apart because the distance first increases. Then they get further. Then until U is equal to V, then they tend to catch up. So this one will not be correct because there is not moving further apart. So the answer is going to be C. So I'm saying since V could be initially or is initially less than U, then the cars will initially get further apart until U equals to until V is greater or equal to U. Okay, so until the velocity for y is greater or equal to U, then they catch up. Then catch up happens. Okay, so that means the answer is going to be B. So here we have rejected A because the acceleration keeps changing. Yet here the gradient is just increasing, which means the velocity is just increasing and it is a smooth curve. So the velocity is increasing. If we were to sketch a graph of acceleration against time, then it would be a straight line, which means constant acceleration. The resultant force acting on an object is slowly increased. Which graph could show the variation with the time t of the momentum p of the object? So we know that force is equal to the rate of change of momentum. So if I make a momentum, which graph could show the variation with time t of the momentum of the object? The resultant force is slowly increased. So F is increased. That means the gradient should increase. So this one is showing a decreasing gradient. So this one means gradient decreasing. Yet gradient should increase. The gradient should increase. This one is wrong because it is showing constant gradient. This one is constant gradient. This one is also, the gradient is decreasing. So this one is a decreasing gradient. So it is only this one which is becoming steeper, even though the gradient is negative. So this is increasing gradient. So the answer is going to be B. because if F is directly proportional to the gradient, then the gradient should increase if the force is increased. An astronaut has a weight of 660 newtons when she's standing on the Earth's surface. The acceleration of free fall is on the surface of Mars is 3.71 meters per second squared. What would be the weight of the astronaut if she stood on the surface of Mars? Okay, so we just need the mass because the mass is going to be the same. So the mass is equal to the weight divided by g, that is 660, divided by 9.81, that is the mass. So the weight on Mars is going to be mass times g, which mass is 660 over 9.81 times g on Mars, which is 3.71. So I'll check with my calculator. 660 times 3.71 divided by 9.81. So that is 249, which is approximately 250 newtons. So the answer is going to be C. So I first got the mass and I use the mass on another planet because the mass remains the same. Lastly, for part 5, a mass m1 traveling with the speed u1 collides with the mass m2 traveling with speed u2 in the same direction. After the collision, mass m1 has speed v1 and mass m2 has speed v2 in the same direction. The collision is perfectly elastic, so it means relative speed of approach, which is velocities to the right positive, velocity to the left negative. So there is no velocity to the left. They're all to the right. So relative speed of approach should be equal to the relative speed of separation. If it is perfectly elastic. So which equation is not correct? Let's check. U2 minus U1, that is relative speed of approach. So V2 is bigger than V1, so we shall say V2 minus V1, that is relative speed of separation. So U2 minus U1 is V2 minus V1. So we are having that V2 minus V1 is the same as U2 minus U1. So it can be V2 plus U1, V2 V2 is positive. No. U1, if collision occurs, then it means U1 must be bigger than U1. So this is going to be U1 minus U2. If collision occurs, U1 is bigger than U2. So that will be U1 minus U2. If after collision this is what is happening, then V2 is bigger than V1. So V2 minus V1 is equal to U1 minus U2. So here I want you to note that U1 is greater than U2 for collision to occur. Yet here V2 is greater than V1 after collision. So the word relative means subtracting. That's why I'm subtracting the velocities. And since they're in the same direction, I can't say minus negative. So V2 plus U2 should be equal to V1 plus U1. So that equation is correct. Then conservation of kinetic energy, we know that. Okay, conservation of momentum, total momentum before collision, M1 U1 plus M2 U2 should be equal to M1 V1 plus M2 V2. That is total momentum before collision. So when you collect M1 into U1, so we have M1 into U1 minus V1 should be equal to M2 into V2 minus U2. So when I simplify this, I get that. So this equation is correct. Then the first equation is as if it is conservation of kinetic energy. Let's check kinetic energy before is a half. So this is momentum. Then this is kinetic energy. A half M1 U1 squared plus a half M2 U2 squared. That is before collision. After collision is a half m1 v1 squared plus a half m2 v2 squared. So a half cancels out. And if I collect like terms, it will be m1 u1 squared minus, I bring m1 on this side to be m1 v1 squared equals to, the other side I have m2 v2 squared minus m2 u2 squared. So this equation is also correct. So this one will not be correct. Okay, let that be the end of part 5. See you in part 6. Bye bye.